Hello students, I am Sumalata. In today's class, I am going to explain about aromatic hydrocarbons. Within less time, one short video. I think you are all trying to watch this video without skipping. You will get good information for your examination. After watching this video, just mention your words in comment box how it is useful to you. If you feel useful, please do subscribe, share to your known people and like. Then we will start our topic. Aromatic hydrocarbons are nothing but aroma giving compounds. Aroma is nothing but good smell in nature, okay? And also if they are going to be combust, they will give sooty flame, okay? These are the general properties, and mainly how can you tell the particular compound is the aromatic compound? By knowing its aromaticity nature. What is aromaticity nature? That is nothing but the compound must possess planarity, nothing but all carbon atoms present in the same plane. And another thing is it should be all pi bonds, I mean delocalization of pi bonds, the second condition. And the third condition is Huckel's rule, 4n plus 2 pi electron should need to be possessed, okay? By following these three conditions, the compound should become a aromatic compound. Especially most of the aromatic compounds having benzene as the part, I mean benzene is the constituent in that molecule. But for few molecules they are having aromatic nature, but they did not possess benzene ring. But following these three conditions, okay? If you take aromatic compounds, I mean in our surroundings, naphthalene balls, you can see naphthalene balls also a aromatic compound that will used as a moth repellent agent, and also used in nothing but toilets, washroom, wash basins, and also used in our cupboards, okay? And also these compounds used in few food industry also, because they are giving good smell, and also used as a giving colorful used as a coloring agent, okay? Coming to, you can see few aromatic hydrocarbons. See, benzene is the parent aromatic hydrocarbon for most of the aromatic hydrocarbons, okay? This is benzene. You can see this is the phenol, OH. See, this is naphthalene. Just now we have discussed about it. This is naphthalene, okay? This is naphthalene. And you can see anthracene. This is the anthracene. And one more thing, phenanthrene, you can see phenanthrene, this one is the phenanthrene, okay? All these are having benzene ring as their constituent, and few things also you can see. This is toluene, CH3 is the toluene. And next one, if you see cyclohexadienyl anion. This is the cyclohexadienyl anion. Next, one more thing, see 1, 2, 3, 4, 5, 6, 7. Cyclohexatrienyl cation. This one. This is cyclopentadienyl anion. Cyclopentadienyl anion. Cyclohexadienyl cation, this one. These are not having benzene ring, but they are having aromatic in nature. Because they possess those three conditions: planarity, next to delocalization of pi electrons, and Huckel's rule, nothing but 4n plus 2 pi electron system, okay? If you want complete information about aromaticity, anti-aromaticity, non-aromaticity, Huckel's rule, you can see one. Actually, I have made that video with detailed information. You can check in playlist, okay? Yes, here these are all comes under as a aromatic hydrocarbons. Okay, then coming to nomenclature of aromatic hydrocarbons and isomers of aromatic hydrocarbons. Actually, we have already seen about nomenclature in our previous class, hydrocarbons. But for with little information, brief information we can say about here. So you can see benzene is the, see benzene, its molecular formula is the C6H6. It was isolated by Michael Faraday in the year 1825. Here, in benzene ring, all carbon atoms are similar, nothing but all are attaches with each other by a cyclic manner, and each carbon atom attaches with one hydrogen atom. So 6 carbon atoms attaches with 6 hydrogen atoms. All these 6 hydrogen atoms are equal. All these hydrogen atoms are equal. So because of this equality, benzene can form only one mono substituted benzene. That means if you substitute one methyl group instead of one hydrogen, okay, so what will happen? Methyl benzene will be formed. This is toluene, I already told you. Methyl benzene will be formed. This is the one single substituted benzene. If you take if another hydrogen on benzene replaced with another substituent, monovalent substituent, then you will get one ortho product, one para product and one meta product. Why? What is the reason behind this one? Why not 2 products? Why not 3 products similar? Nothing but why not 2 ortho products, 2 para products, 2 meta products? The reason, because here, see here it is the already this hydrogen substituted. So this hydrogen and this hydrogen are similar with each other. This hydrogen and this hydrogen similar with each other, so that we can call these 2 positions are ortho. And also this hydrogen and this hydrogen similar with each other, we can call these positions are meta positions, and this one is the para position. So that if you substitute these positions with another substituent, that means you can give numbering here. This is first one, second one, third, fourth, fifth, sixth. So if you substitute with any group here, second position or sixth position, that nothing but C1 and C2 equal to the C1 and C6, nothing but 1,2 dimethyl benzene, nothing but orthotoluene, that is equal to the 1,6 dimethyl benzene. See, I am writing here. If the second one replaces with one more methyl group, so you will get, see, this is the orthotoluene. This one is similar to the this one. This one is similar to the this one. Why? Because both are similar, because I am explaining that one also why these are similar. And you can also observe this one, meta positions. See here, this one and this one similar to the this one. See, these 2 are similar with each other, and one para product is there. See, so okay, if the substituent is second position or sixth position, similar. If substituent is third position or fifth position, similar. Okay, listen. Yes, this is about nomenclature. Then we will move to what is stability of benzene, if you see, and why, how can you give if the how can you identify benzene have 3 double bonds? That one was identified by if benzene reacts with ozone, that will form triozonide. See, you can observe this reaction, triozonide. So it will conforms the benzene having benzene having 3 double bonds in its structure. This triwosanide confirms about benzene having 3 double bonds in its structure. Okay, this is the triwosanide. This one, that means the presence of triple 3 pi bonds in benzene gives the unusual stability to the benzene. And that one also, how these 3 pi bonds going to be arranged in benzene ring, you can see. Generally, Kekule proposed 2 structures for benzene. Those are nothing but resonance hybrids of benzene. How he is going to be proposed? He was proposed that one. First one, you can observe about what is the hybridization in carbon. In benzene, the carbon involved in sp2 hybridization, so that each 6 carbons are there. Each and every carbon going to be involved in sp2 hybridization. That means one carbon having 3 sp2 hybrid orbitals, so that each carbon going to be involved in bond formation with 2 adjacent carbons, nothing but by using 2 sp2 hybrid orbitals. Remaining 1 sp2 hybrid orbital involved in bond formation with hydrogen, and remaining unhybrid p orbital going to be involved in p bond formation. P bond is nothing but pi bond formation. Okay, you can see like this. Suppose this is the I am writing middle, okay, for easy understanding. This is the benzene ring. Here one carbon, one orbital, this is another orbital, this is another orbital. See, okay, here one okay, here also, here also, here, okay. See, these hybrid or 3 hybrid orbitals are there. Each, listen, these hybrid or sigma bonds are formed by overlapping of sp2 hybrid orbitals, overlapping of sp2 hybrid orbitals for adjacent carbon atoms. Okay, you can see this one. Yes, okay. Then after this is the third hybrid orbital, sp2. This is the hydrogen, and here also this is the hydrogen. This is the hydrogen, this is the hydrogen, okay. The remaining unhybrid p orbitals are there here. See, these unhybrid p orbitals going to be overlap, sideways overlapping. See, this one, okay. Listen, here it is. So if the overlapping is happens like this, benzene ring becoming here one double bond, here one double bond, okay, like that. If the overlapping is happens like this, see, here first we have seen here overlapping, okay. That is not like the, see, that overlapping takes place next time here, okay. So that will be reverse for these two and these two, so that you will get another benzene ring, that is see, the double bonds going to be formed like this. This one and that one, these two structures are similar with each other, so that Kekule proposed these see, this structure and this structure, these two structures are also known as Kekule structures. So that for these two structures, by introducing a circle, dotted circle or complete circle in a benzene ring, will indicates the delocalization of pi electrons, delocalization of pi electrons in benzene ring. Okay, that means these pi bonds are not fixed for a certain position. They are going to be delocalized from one place to another place. Nothing but, see, here one carbon is there, here one carbon, here one carbon. The bonds, say, the electrons present in carbon sigma bond are more strong but the electrons present in pi bonds are not much strong. I mean, they are not much stable to sit one place, so that they are going to be attracted by the adjacent carbon atoms nucleus. So that what will happens here, um, the double bonds position will be changed. See, you can observe here that structure. See, same structure, this one and this one. So if these pi bonds are going to be shifted like this, then you will observe like this. See this structure and that structure, so that the unusual stability of benzene gives same I mean single substituted benzene. I already told you, mono substituted benzene, and also only one ortho substituent, only one one meta substituent will, para will also be only one, but only one ortho and only one para will be formed because of the unusual stability of benzene, and also oscillating double bond. We can call this one as a oscillating double bond. This is the reason benzene can show these two type of structures, and that one, because of this oscillating double bond nature, benzene can form only one ortho substituted product, one meta substituted product. Para will also be only one product only. Okay. Then coming to why benzene can't I already told you in previous classes, those are detailed explanations. So that's what I told you for every time, again and again I already told you. Okay, actually benzene mainly involved in substitution reactions only, not in nothing but addition reactions. What is the reason? If benzene involved in addition reactions, the benzene loses its aromaticity. That is the reason it will going to be involved in addition reactions. And one more reason, what is the reason behind this one? Because of oscillating double bond nature. That means pure double bond or pure pure double bond only. Pure double bond is absent here. That is the reason benzene can't able to involve in addition reactions. If it is involved, it will lose its aromaticity. Okay, by seeing this one, we may think benzene have 3 triple bonds, so that all double bonds. Now, here see, these this is one double bond, this is one double bond, this is one double bond. Okay, and this is the single bond, so that all are having same bond lengths, but those bond lengths are different with each other. Why they are different with each other? Here double bond, single bond, if you take 154 picometers, double bond is the 134, I think 134, yes, it is 134 only. 139, it is not 134, 139 picometers bond length will be shown. Now, because of these two different bond lengths, what is the reason here? Here the reason is absence of pure double bond. Here also same reason, absence of pure double bond. That is the reason it will not show same bond length for all bonds present in the benzene ring. Then we will move to discuss about chemical properties. Physical properties, we are already we know these are all maximum liquids. If they burn, they will give sooty flame, and also they are good smelling agents. These are also known as arenes. Then these are also used in disinfectants, disinfectants. Example I told you, naphthalene balls. Okay, these are all comes under as a physical properties. Then chemical properties. Chemical properties, if you see, especially substitution reactions. These substitution reactions, I think 6 to 7 reactions are there. Then after, if involved in addition, then what will happen? Okay, then we will move to chemical properties. Preparative methods of benzene, if you see, benzene first of all commercially prepared by the coal tar. If you take laboratory preparation methods, in laboratory preparation methods, cyclic polymerization of ethane molecule you can take, that is CH triple bond CH, you can take 3 moles, then it will gives you benzene ring. This is the benzene, okay. Cyclic polymerization of ethane molecule, this one, this is the first one. And the second one you can take decarboxylation of sodium salts of benzoate. Sodium salts of benzoate you can take like this, benzene ring, on that one CO, instead of H you can write Na. This is the sodium salts of benzoate, and this will going to be decarboxylate in presence of soda lime, that is the NaOH plus CaO. NaOH with CaO is the soda lime, CaO, okay. Then you will get benzene. Along with this benzene, decarboxylation takes place in the form of Ca2CO3, okay. And the third preparation method is reduction of phenol. You can see phenol vapors you should pass on the zinc dust, then it will gives you under high pressure and temperature. Here you are using so benzene will form and zinc oxide along with this also, okay. These are the 3 preparative methods, and then we will move to chemical reactions of benzene. Especially we are discussing about substitution reactions, because benzene mainly involved in substitution reactions. If it is going to be involved in addition reactions, it will lose its aromaticity. That is the reason mainly we are discussing here substitution reactions. Along with those reactions, we will discuss few addition reactions also. Now we will move to substitution reactions. In substitution reactions, especially we are going to discuss about nitration, sulfonation, alkylation, halogenation, acylation, acylation, okay. That will comes under this one only, okay. All these reactions followed by the formation of carbocation. This carbocation going to be attack on a benzene ring. How they will happens, you can see here. First one, the first reaction is nitration. You can take nitration. In nitration, benzene reacts with nitrating mixture. You will get nitrobenzene. See, benzene react with nitration mixture. What is the nitration mixture here? Concentrated HNO3 plus concentrated H2SO4 will be the nitrating mixture. Here you are using 323 Kelvin to 333 Kelvin temperature we are going to use. Then you will get nitrobenzene. This is the nitrobenzene. First of all, here while observing mechanism, you will get nitrosonium ion. That nitrosonium ion going to be attack on this benzene ring. The next reaction is halogenation. You can see halogenation. Here in this halogenation, benzene reacts with halogens, especially chlorine, bromine, in presence of Lewis acids like anhydrous AlCl3, FeBr3, FeCl3. Those are acting as a Lewis acids. You can take that reaction. This is the benzene reacting with chlorine or bromine, anhydrous AlCl3. I am taking Cl2 gas here. So chloronium ion will be formed. That chloronium ion attacks on this benzene, so that chlorobenzene will form. This is the chlorobenzene, this is the nitrobenzene. Okay. The next one is third one, sulfonation. If you take sulfonation here, benzene heating with fuming sulfuric acid, that is also known as oleum, okay, then it will form benzene sulfonic acid. You can see that reaction here. This is the benzene. This will going to be reacting with fuming sulfuric acid. H2S2O7 is the fuming sulfuric acid. Fuming sulfuric acid also known as oleum. Okay, this will gives you benzene sulfonic acid, HSO3. HSO3 will going to be attack on benzene. Benzene sulfonic acid will be formed. In the same way, you can go to next reaction, that is alkylation. Alkylation also happens if benzene reacts with alkyl halides, then it will form alkyl benzene. That alkylation takes place in presence of same anhydrous AlCl3Fe, Cl3Fe, Br3. Okay, so you will get here, you can take, this is the benzene. I am writing CH3Cl, methyl chloride I am taking here instead of alkyl halide. So, so anhydrous, in presence of anhydrous AlCl3, I am getting chlorobenzene. Not chlorobenzene, sorry, methyl benzene, because here we are getting alkyl benzene, so that methyl benzene. This is also known as a toluene. This is also known as a toluene. Okay, next we will move to remaining preparation, remaining chemical properties. If you take same alkylation, just now we have seen about methyl chloride. If you methyl chloride will gives you methyl benzene. If you take ethyl chloride benzene you will get. If you take propyl chloride, if you take, what is the product here, you need to understand. Is it the product is here N-propyl benzene or isopropyl benzene? The product is here isopropyl benzene. What is the reason here? Because hydride shift going to be takes place. That is the reason secondary carbocation will be the more stable when compared to the primary carbocation. So that secondary carbocation going to be attack on benzene ring. That is the reason you will get the major product is the isopropyl benzene. So that I am writing that one only. You can see this is the benzene reacting with CH3, CH2, CH2Cl. This is the propyl chloride in presence of anhydrous AlCl3. So you will get the product is here. This is benzene ring. On benzene ring, secondary carbocation going to be attacked, so that isopropyl benzene will be formed. This is the isopropyl benzene. This is the major product instead of N-propyl benzene. Okay, then coming to next one, fifth one, acetylation. If you see acetylation, benzene reacts with acetyl chlorides or anhydrides, acetic anhydride or acetyl chlorides, then you will get acetyl benzene. Okay, or acyl benzene. See, you can take this example, CH3COCl. This is the acetyl chloride. So here you will get the product is here acetophenone is the product, C double bond O CH3. Okay, CH3CO plus ion formed, that ion going to be attack on the benzene ring. Okay, and the next one you can take anhydride. The same is acetophenone will be formed. See, here I am writing like this, plus CH3 C double bond O C double bond O CH3. This is the acetic anhydride. This acetic anhydride also forms see, electrons going to be this side. So CH3CO plus ion will be formed. That CH3CO plus ion attacks on here. So you will get the product C double bond O CH3. Here also acetophenone. The remaining byproduct is the acetic acid, CH3 COOH is the acetic acid. There the product is the HCl will be the product, HCl. Okay, these are the chemical reactions of nothing but especially substitution reactions. If in case if I am taking extra chlorine, excess of chlorine or halogens, what will happens? You can see I am taking, see here it is the benzene. It is going to be reacting with 6 moles of Cl2. 6 moles of Cl2. Cold and dark conditions. Cold and dark conditions. You will get all hydrogens going to be substituted by the chlorine. So you will get hexachlorobenzene, Cl, 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 Cl. This is the hexachlorobenzene. All hydrogens going to be substituted by the chlorine atom along with the 6 moles of HCl, hydrochloric acid, will be formed. Its molecular formula is the C6Cl6. Now generally benzene molecular formula is the C6H6. So here you can write a C6Cl6. Okay, these are about substitution reactions. If you move to the addition reactions, what will happen? You can see about addition reactions. Addition reactions, if benzene involves in addition reactions, it will loses its aromaticity. So that you can write, you can observe these reactions. First one is, if benzene reacts with hydrogen at high temperature or pressure, nickel as a catalyst here, so all double bonds going to be reduced by hydrogen atoms. So you can see that reaction. This is the benzene ring. If it is going to be reacting with hydrogen, okay, hydrogen, nickel as a catalyst under high temperature or pressure. So thermal heat I am taking here. So benzene becomes cyclohexane. Cyclohexane. This is the cyclohexane. All double bonds going to be reduced. All double bonds going to be reduced here. Then one more condition you can also see. If benzene reacting with chlorine in presence of UV light and 500 Kelvin temperature, all double bonds going to be added by chlorine atoms. Okay, chlorine atoms going to be added instead of these double bonds broken up, and then chlorine atoms going to be added. This one is known as the benzene hexachloride. Previous case we have seen a hexachlorobenzene, but that is different, this is different. This is the benzene hexachloride. So is this one also known as gamma-xime. This one also known as gamma-xime. XIME. Okay, gamma-xime. Next one, one general combustion reaction you can see, C6H6, benzene heated in presence of air, then you will get carbon dioxide. This is the heating, you will get 6 moles of carbon dioxide and 6 moles of water molecules. Okay, you can see this is not 6 moles, so this is 3 moles because we have taken 6 hydrogen atoms only. Okay, these are about addition reactions of benzene. One more thing, if you take, actually generally till now we have seen about substitution reactions. All those substitution reactions happens by the substitution of electrophile. Nothing but electrophilic substitution reactions are taking place on a benzene ring. How these reactions, these reactions are favored by the which group? If you want to know, you need to know about directive influence of groups present on benzene ring. So that I'm trying to, actually I have done previous few videos about directive influence of groups on benzene ring. You can check there, detailed with detailed explanation is there, so that I'm trying to tell 2-3 points here only, okay. So here you can take if benzene ring is there, if it is going to be attached electron donating groups, see electron, see this is the benzene ring, electron donating groups A, it is A, just imagine this A is a electron donating group, then it will become the electrophilic attack mainly takes place on ortho. See, this is the ortho position. See, this is ortho position, ortho as well as para position. The electrophilic addition, electrophilic substitution takes place on ortho and para positions. If the, okay, for this one you can take a few examples. OCH3 methyl, next you can see few examples about this one. Amino group, NH2 group, and substituted amine, NHR, okay, amide, NHCO, NH2, this one also, and then ethyl, C2H5, and so on, etc. These are the electron donating groups. That means these groups are the directs electrophiles towards the ortho and para positions, okay. And then coming to if benzene ring attaches with electron withdrawing group, see EWG, electron withdrawing group. Here electron, if instead of A you can write E, electron donating group, EDW, okay, for shortcut, okay. Yes, if electron withdrawing group is there, the electrons rich the position is the meta position. So it is taking electrons from the benzene ring, so that you will get electrophilic substitution on meta position. This is the EWG. So here also EDG, okay. Here it is the meta position, so the electrophilic substitution here also, maybe here are there, electrophilic substitution takes place on these two positions are nothing but both are similar only, okay. You can see some examples about this one. Here I am writing NO2 nitro group, aldehyde group, next COR, nothing but ketone, next acid, next ester, COOR, okay, next, and CN, yes, CN, and so on, okay. All these groups are going to be withdraw electron from the benzene ring, so that they will direct the electrophilic substitution on a meta position, okay. Electron withdrawing groups on a electron donating groups on ortho and para positions, withdrawing groups on a meta position. That means they will favors the electrophilic substitution, okay. This is about nothing but aromatic hydrocarbons. I think you all understand about this one. Please, if you feel useful and informative, do subscribe, like and share these videos to your known people. We will meet in the next class. Bye, I love you.